Welcome to the second chapter of my series on my personal exploration with squircles. This video is going to be a brief introduction to the p-norm. The p-norm was invented by Hungarian mathematician Frigyes Riesz. Most of you are probably familiar with what's called the Euclidean norm, where the length of a vector in n-dimensional space is the square root of the sum of the squares of its components. The p-norm, however, is defined as the pth root of the sum of the absolute value to the p's of the vector's components. This then means that the Euclidean norm can also go by the name of the 2 norm. There are certain properties that all norms must have. The first is that any norm n must be non-negative, which means the norm or length of any vector is greater than or equal to 0. The second is that the norm must be absolutely homogeneous, which means that constants can be taken out of the norm within an absolute value. Third is that the norm must be positive definite, which means that if and only if the norm of some vector is 0, then that vector is the 0 vector. Finally, a norm must be subadditive, which means that it satisfies the triangle inequality. In other words, the distance directly between two vectors is less than or equal to the distance traveling along both vectors. If we say that this norm n is the p-norm, we can see that it satisfies the first three properties, but the norm is only subadditive if p is 1 or greater. When p is between 0 and 1, the p-norm actually becomes what's called a quasi-norm. Taking this definition, we can rewrite our equation for a unit squircle in terms of the p-norm. In fact, we can generalize this to squircles of any radius r sub p, and this new equation, once simplified a bit, can make more sense of what a squircle is. A squircle of radius r sub p is the set of all points xy such that the p-norm of xy is r sub p. Bringing this to the hypotenuse function, it can also be written as the reciprocal of the p-norm of cosine and sine. Another important property of the p-norm is that every greater p-norm is less than the last for all positive p. A good way to start getting intuition with this fact is by taking height base p. Since height is the reciprocal of a p-norm, it actually increases when p does, just as the boundary of a squircle increases as p becomes greater. From that, it's possible to understand that the p-norm decreases when you increase the value of p. And as p goes to infinity, the p-norm becomes the maximum norm, also called the infinity norm, the Chebyshev norm, uniform norm, or supremum norm. The maximum norm of a vector returns the component of the vector with the greatest absolute value. Visualized, our squircle becomes a square. And here's the equation for a unit square with a radius r sub p. In the next video, we'll explore the maximum norm in combination with base p trigonometry. See you in the next one!